Right now, while you are reading these lines, something is happening on a dry mountainside west of Madrid that almost no one on Earth knows about. 6 giant radio antennas are simultaneously turning toward the same point in the sky, not to guide a rocket, not to catch a satellite signal, only to listen. 24 billion kilometers from where you are sitting, a machine is whispering toward Earth. It was built before the internet existed, before home computers existed. It runs on about 4 watts of power. The light inside your refrigerator uses more electricity than that. And this tiny ancient machine is sending back a signal that researchers are not describing with words like interesting or surprising. They are using words like astonishing, unprecedented, and we were wrong. This is the story of Voyager 1, of its last year, an instrument named PWS, of the hum that is growing louder in the space between the stars, and of a day locked into the calendar, the 18th of November this year, that will mark the moment no human civilization has ever reached. Subscribe right now, because we have only just begun. Go back to the middle of 2017. A small science office on the campus of Cornell University in the state of New York. A doctoral researcher named Stella Koch-Ocker is sitting in front of a computer screen looking at a frequency spectrum graph from the PWS on Voyager 1. Her task is simple and modest. Filter the data, find the known plasma whistle's short oscillation events that appear once or twice a year when solar storms sweep out to the edge of the system, and create shock waves in the interstellar plasma. Record them. Add them to the density map the scientific community is slowly building. It would be a small, useful contribution, a piece of data for a doctoral dissertation. But there is a faint line, a thin, almost invisible band running across the graph between the whistles. It just sits there. It does not turn off. It does not change noticeably. It simply exists. She sits still looking at it and wonders whether she is beginning to imagine something that is not there. In science, that is the most ordinary question. You look too long at data, and you start seeing patterns where there are none. But she checks again. Then she pulls the data from 6 months earlier, 1 year earlier, 2 years earlier. The faint line is still there. It has been there since the middle of 2017. To understand why this matters, you need to know what the physical models had predicted before Ocker. For decades, plasma physicists had built detailed models describing the space between the stars. Not guesswork, the work of the best minds, still living, peer-reviewed across generations, and all of them agreed on one point: the interstellar plasma was supposed to be a relatively silent cosmic waiting room. Extremely thin, extremely cold, particles drifting slowly. No mechanism that could produce a continuous, stable, narrowband plasma wave signal lasting for years. Before Ocker, the only way to measure interstellar plasma density was to wait for solar shock waves. Since the spacecraft entered the interstellar region, there had been exactly 8 such events in more than a decade. 8 data points. Like trying to understand the weather of an entire continent by looking at a single thermometer in a single city once a year. Then Ocker found the faint line. Suddenly, humanity had a continuous data stream. Not 8 points, but thousands of points every week. On the 10th of May, 2021, the journal Nature Astronomy published the paper by her and her co-authors Cordes Chatterjee, Gurnett, Kurth Spangler. The title is as dry as every serious scientific paper, but beneath it lies a statement that breaks a model. Not a burst, not a glitch. A continuous signal, year after year. We were wrong. And the pitch of that hum is rising, steadily, without pause. Why that is where the story becomes physical. Here I have to stop and explain something fundamental, because if you do not understand this, you will not understand why this story is urgent. The hum of the PWS is not sound in the sense that human ears hear. It is an electric field oscillation in the plasma at a frequency of a few kilohertz. When scientists convert this signal into audible sound for the public, as in the NASA video sounds of interstellar space, they simply shift that electric frequency into the audible range. But the underlying physics is precisely beautiful. The plasma frequency is proportional to the square root of the electron density. In other words, the higher the pitch climbs into higher frequencies, the greater the density. Listening to the hum climb is measuring the electron density around Voyager increasing. And here is the number JPL announced in May 2021 at the press conference after the Nature Astronomy paper came out from 2013, when Voyager left the protective bubble of the Sun. To the middle of 2015, the electron density around the spacecraft had increased by about 40 times. 40. Not 2, not 10, 40 times denser. Ocker described it in exactly these words in an interview. Basically, it is a pure tone. And over time we do hear it change, but the way the frequency is shifting is telling us how the density is changing. This is the physical meaning of the phrase getting louder in the title of this video. Not greater volume, higher pitch, greater density. The plasma wall in front of Voyager is becoming more crowded, steadily, gradually enough that the hum the PWS is catching keeps climbing into higher frequencies. You are not hearing greater volume. You are hearing the plasma thickening around the spacecraft. And what Ocker and her team have opened is the ability to read this change in real time. Not waiting 3 years for a new data point. Reading every day. Hearing the pitch climb as density increases. Co-author James Cordes at Cornell likes to compare the interstellar environment to an ocean. Before Voyager, we could only observe the surface from the shore. Ripples rose when there was a storm, but when there was no storm, the sea surface was silent, and we did not know what lay beneath. Then a solar shock wave arrived, a thunderstorm passing through, and we got a brief glimpse into the depths. Then back to silence, then waiting again. Cordes says Auker's hum is like discovering that the ocean has been whispering the whole time, not only when there is a storm, right now. And the whisper carries information. He said in the 2021 NASA press conference, in the case of a solar outburst, it is like detecting lightning in a thunderstorm, then it returns to a gentle rain. The gentle rain is the hum, it is continuous, it is simply there. And in every raindrop there is information about the space the spacecraft is swimming through. Auker sealed this with a sentence I think deserves to be written into the history of science. She told JPL the spacecraft is saying, "This is the density I am swimming through right now, and this, and this, and this, word for word. This is the real treasure. Not a discovery, not a spectacular data point. A continuous stream about the location, condition, and change of an environment humanity has never measured from the inside, right now, right while you are breathing." Voyager 1 is sending us how the interstellar plasma is breathing. Before Auker we had snapshots, after Auker we have a movie. But this is where the story stops being abstract and touches Earth. Now I need you to sit up straight, because the next part is no longer abstract. It touches here. The place where you live. Our solar system is wrapped in a structure I will simply call the protective bubble. It is a gigantic bubble created by the solar wind, a stream of charged particles blowing outward from the sun in every direction, pushing back against interstellar space, creating a buffer zone that contains our entire solar system inside. The outer edge of that bubble has an official name in physics, but that is not the story of this video. The story of this video is what is pressing against that edge from the outside. For decades, physicists assumed that the interstellar plasma pressed against our bubble with a fairly stable pressure. Enough to shape the bubble into a certain form, but nothing dramatic. Then Voyager began sending back data. And what the PWS, together with accompanying magnetic field measurements, is showing is that pressure is not stable at all. It has a rhythm, it has surges, it has large structures lasting years that press against our protective bubble in ways no model ever predicted. Voyager has detected deformation waves on the surface of the bubble that can reach sizes of 10 equivalent to 10 times the distance from Earth to the Sun, about 930 million miles. These are not small waves. These are structures the size of the entire inner solar system. Our protective boundary is continuously moving, not static, not stable. Voyager has also detected that the boundary undergoes rapid changes over very short timescales, changes that contradict existing scientific models and remain unexplained to this day. Why does this matter to you, the person breathing Earth's air? Because that bubble is a shield. It deflects most of the high-energy cosmic rays, particles accelerated by stellar explosions and other violent events in the galaxy before they reach the inner planets. Earth's biology evolved under that shield. Your DNA could not withstand the full radiation flux the galaxy blows in. If that shield is moving more strongly than we ever thought, the implications for long-term life on this planet are worth questioning, not panicking, questioning. It is not only that density is increasing, it is an entire living surface moving in ways no model predicted. And the hum is the only tool that can read its rhythm. And this is how seriously humanity is treating this hum right now. Go back to Madrid, the 20th of April 2024. The Madrid Deep Space Communication Complex is one of 3 antenna complexes NASA uses to communicate with the farthest spacecraft Goldstone in the United States, Canberra in Australia, Madrid in Spain, spaced evenly around Earth, so that no matter how the planet turns, there is always at least one complex that can see the spacecraft. The largest antenna at each complex is 70 meters in diameter, a collecting surface larger than a football field. That day, for the first time in NASA history, all 6 antennas of the Madrid complex were arrayed simultaneously to receive the signal from Voyager 1. The technique is called arraying, combining the collecting surfaces of multiple antennas into one giant virtual ear. The natural question is, why do this now? NASA gave the direct reason in the documentation accompanying image PIA 26147. Currently, a 5-antenna array is required to downlink science data from the PWS. Read that sentence again. 5 antennas. At the same time, just to hear the hum. To help you understand why so many are needed, Voyager 1 transmits its signal back to Earth with a 22.4-watt transmitter equivalent to a small light bulb in a refrigerator. When the signal has traveled 24 billion kilometers and finally reaches an antenna on Earth, the power has dropped to 10 to the minus 16 watts. The electronic watch on your wrist operates at a power level 20 billion times stronger than that. No single antenna can catch it. Arraying is required. The entire complex must be mobilized. The computer inside Voyager 1 runs about 81,000 instructions per second. The smartphone you are holding is 7.5 million times faster. Yet that machine is sending back news that no supercomputer on Earth could discover on its own. 9 years ago, a doctoral student sitting in a university office saw a faint line in the data and wondered whether she was imagining it. Today, to keep listening to that faint line, humanity turns 6 giant antennas on a Spanish mountainside simultaneously toward one point in the sky. Not for a major event, not for a new discovery, only so as not to miss today's update of the hum. That update, after exactly 23 hours of light travel time, will arrive at the computers at JPL. Scientists will open it, compare it with yesterday. Has the pitch climbed? Has anything anomalous appeared? Then store it in the planetary data system to sit beside every previous update, a stream that can be read again years after Voyager is gone. 6 antennas. At the same time, just to hear a signal that your wristwatch is 20 billion times stronger than. But there is something the hum has already caught, and no mainstream news is telling. In the middle of 2020, when Voyager 1 was at a distance of 149.0 from the Sun, its hum changed. Not a small shift. A sudden jump. Over about 8 days, the frequency of the hum pushed upward, and in parallel, the magnetic field measurements from the magnetometer instrument on the spacecraft also recorded an equivalent increase in magnetic field strength. Both quantities increased by about 1.36 times. At the same time, at the same location in space, the same structure. Scientist Leonard Berlage, a major figure in Voyager research, together with his team, published these results in the Astrophysical Journal, number 953, page 135, in the year 2023. They named the structure magnetic hump. And they noted something even more remarkable. After the initial jump in July of 2020, the magnetic field strength continued to rise, more slowly but without stopping. It reached a maximum of about 0.56 nanotesla in early 2021. Then it gradually declined, back to the post-jump value by the end of that year. The entire event lasted 1.5 years. And according to the most recent paper by Berlage's team, published on IOP in May of 2026, the magnetic field strength remained higher than the pre-event level until the middle of 2025, meaning the hump has not fully ended. This is what makes the structure strange. It is not a shock. Shocks usually pass quickly, a few hours, a few days. It is also not a random fluctuation. It has a shape. It has a beginning, a peak, a close. It lasted 18 months. And both Auker's hum and Berlage's magnetic field recorded it simultaneously, meaning whatever passed by Voyager 1 in the year 2020, it was a real structure tens of awe in size, carrying both denser plasma and stronger magnetic field at the same time. The leading hypothesis about its origin, the Sun. During the declining phase of solar cycle number 24, there were very large eruptive events on the stellar surface. Some scientists believe those events created a globally merged interaction region that propagated outward through the solar system, crossed the protective boundary, and injected energy into the interstellar plasma. If correct, the magnetic hump is the trace. Physical evidence that the Sun still has the ability to reach Voyager 1 even though it has been outside the bubble for nearly a decade. But that is only a hypothesis. No one is certain, and there is no way to confirm it except by waiting for Voyager to continue measuring and hoping. What I want you to record is this: the hum saw the magnetic hump. Its pitch jumped throughout the event. If Auker had not discovered the hum in the year 2017, we would have Berlage's magnetic field record without the corresponding plasma witness. We would have half the story. The PWS is the only witness, the unique instrument that can confirm the structure the magnetometer detected. Without the PWS, only half the story. Then comes the newest and possibly most unsettling discovery. In January of 2024, William Kurth, together with his team, published a paper in the Astrophysical Journal Letters with a conclusion that, in the dry language of science, reads almost like a statement of surprise. I quote the key sentence verbatim: "Since the pressure event of 2020, the density has remained relatively stable at about 0.147 electrons per cubic centimeter, suggesting that Voyager 1 has reached a broad density peak and possibly a new regime. New regime. Not the next region. Not a slight change. New regime." In the language of plasma physics, that word carries weight. It means the rules governing the environment may be different. That what Voyager is swimming through now is not a simple extension of what it passed through in the first 7 years beyond the boundary. It is something else, with its own properties, possibly with a different origin, and no one knows for sure. What makes this even heavier is that Kurth's 2024 data comes from Auker's hum itself together with the accompanying quasi-thermal noise line. That is, the density measuring tool. Voyager 1 has now reached a distance of 161.40 from the Sun, a distance no other spacecraft has ever attained. And at that distance, the plasma density has stopped increasing steadily. It has leveled off at 0.147 electrons per cubic centimeter, stable for several years. The big question is stopped because of what shape does the plasma wall in front of Voyager, if we can call it that, have Kurth's team published the companion paper for the official dataset on the 3rd of November 2025 in the Astrophysical Journal Supplement Series number 281, Article 16. This dataset is now available on NASA's Planetary Data System, an archive any scientist in the world can access. It is a detailed transcription of every frequency of the hum, every density inference, every data point Voyager has sent back since it entered the interstellar medium, and it will continue to be updated as long as the PWS remains alive. Only that long. There is one more detail I want you to keep. Donald Gurnett, who has been the principal investigator of the PWS instrument on both Voyager spacecraft since they launched, offered a prediction in an interview with PNAS in the year 2021. He said that if he had to guess, the density might continue to increase to a peak, then decrease slightly again. He compared it perhaps the interstellar material is piling up in front of our protective boundary like snow piling up in front of a snowplow. If Kurth 2024 is correct and Voyager has reached the peak, then Gurnett was right. But the next question, whether the density will decrease, and when, and by how much, no one has enough data to answer. Only the hum, if it continues to measure, will tell. New regime. In the language of plasma physics, that word carries weight. And now we come to the present, because the present is tighter than you think. On the 17th of April 2026, the Voyager team at JPL received a difficult decision. One of Voyager 1's science instruments, the low-energy charged particle detector, had to be turned off. Not because it failed, still working well after 49 years. Turned off because the electrical power had dropped below the level needed to sustain all remaining instruments at once. Choose one to shut down. The team chose this instrument, because the two remaining instruments, the magnetometer and the PWS, cannot be replaced. Kareem Badruddin, project manager for the Voyager mission at the Pasadena laboratory, spoke in the official press release. He said, and I quote, "Voyager 1 still has two science instruments operating, one that listens to plasma waves and one that measures the magnetic field. They are still running very well, sending back data from a region of space no human-made spacecraft has ever explored. The one that listens to plasma waves. That is the PWS, that is the ear listening to the hum. In February of 2025, the team turned off the cosmic ray subsystem. In April of 2026, they turned off the low-energy charged particles. NASA's publicly updated instrument status board now has 7 X marks 3 remaining check marks. Then 2. Voyager 1 currently produces 57% of its original electrical power. It loses 4 watts each year as the plutonium decays. 48 years after this spacecraft was launched, the hum is the most important thing it can still send back. Not images that cameras were turned off in 1990, not cosmic radiation that instrument was turned off in February of 2025. Not low-energy particles just turned off, only the hum and the accompanying magnetic field. Each shutdown takes away a sense. The PWS is the ear, and the ear is what remains. But the JPL team is not about to give up. Right while you are watching this video, there is an internal project at Pasadena that they call by its own name, Big Bang, an effort to restructure how power is allocated across the still operating systems. If the reallocation is done correctly, it may squeeze out a few more watts. Those few watts mean 1 or 2 more years for the PWS, thousands more hum updates. The team is cautious, the risk is real. Therefore, the team is testing first on Voyager 2 in May and June of 2026. If safe, they will try it on Voyager 1 no earlier than July. And this is not the first time the team has saved this spacecraft. On the 14th of November 2023, the flight data subsystem on Voyager 1 failed. For many months, the spacecraft sent back only streams of meaningless binary numbers. The memory chip had been physically damaged after 46 years of cosmic radiation. The team began rescue operations, moving code to other memory regions. Each command takes 22.5 hours to arrive, plus as many hours again to receive the response. The team succeeded. By June of 2024, Voyager 1 was sending full data again. Voyager is the spacecraft that has been saved once. Big Bang is the second time, but this time not to save the spacecraft, to save the hum. And now comes the moment locked into the calendar. There is a day already written into the calendar. It cannot be changed. At 2 hours, 16 minutes, 7 seconds in the morning Pacific time, on the 18th of November 2026, Voyager 1 will reach a distance of exactly 1 light day from Earth. A signal traveling at the speed of light will take a full 24 hours to go from Earth to the spacecraft, and the same number of hours for a reply to return. No human-made object has ever reached that distance, in the entire history of civilization. On that day, Voyager 1 will cross that threshold while still alive, still transmitting, still sending the hum home. At the beginning of 2026, it is already about 23 hours. By the 18th of November, it will be exactly 24 hours. After that, 25 hours, 26 hours, and so on. There is no way to shorten the distance. Only wait. Only listen. Only record each update when it arrives, knowing that it is a letter from a past we cannot answer in time. From that day forward, everything Voyager 1 says to us is the trace of a yesterday that keeps receding. Now I need you to hold two images in your mind at the same time. The first image, the hum arriving from Voyager 1, traveling 24 hours before it reaches Earth. Then on some day in the early 30s, the final hum will complete its journey home, be recorded, and there will be no next update. The PWS will have been turned off before that. After that day, silence. The last ear humanity has in the interstellar plasma will stop listening. The second image, 48 years ago, when Voyager 1 was assembled in the clean room at Pasadena, a small team led by Carl Sagan bolted onto the body of the spacecraft a gold-plated copper disc, the Golden Record. On the disc are 115 images of Earth greetings in 55 languages, 90 minutes of music from many cultures, 21 recordings of natural sounds, ocean waves, wind, human laughter, and a map drawn from the positions of pulsars that precisely locates Earth in the galaxy. That record does not run on electricity. It has no part that can fail. It is gold-plated copper. It exists simply by existing. When the PWS turns off in the 30s and the hum stops arriving, that disk will still be there bolted to the spacecraft traveling 38,000 miles per hour into the dark. In another 40,000 years, Voyager 1 will drift near a star in the constellation Camelopardalis. It will still be there when the Vietnamese language you are hearing has gone extinct. It will still be there when the sun swells into a red giant and swallows Earth. Two directions of travel, two kinds of silence. The hum coming from outside will fall silent in a few more years. The golden record going outward from us will never fall silent. The first is a scientific treasure that is vanishing. The second is the most permanent thing we have ever made, the same 4-watt machine. But there is a scientific question that remains unanswered, and if the PWS turns off before someone answers it, the question will stay open for many decades. There is a scientific question that the plasma physics community has not answered, and if the PWS turns off before someone answers it, the question will stay open for many decades. Why the hum exists. Two competing hypotheses. The first hypothesis, the plasma oscillations, are thermally excited, naturally consistent with existing physical frameworks. The second hypothesis is called quasi-thermal noise, or QTN. If correct, the current models of interstellar plasma will have to be revised substantially. Not discarded, but many chapters rewritten. To distinguish the two hypotheses, scientists need additional data from Voyager 1 itself, which is producing less each year, or a new mission designed specifically for interstellar plasma. That mission does not currently exist. It is not funded. NASA has the IMAP mission about to launch, but IMAP will remain inside the heliosphere. It will not cross the boundary. The next spacecraft that could actually reach that region, if designed and launched today, would take at least 25 years to arrive. When Voyager 1 falls silent in the early 30s, the real-time window into interstellar plasma closes for at least a generation. No such mission exists. No such mission is funded. So this is what I want you to carry with you. Right now, there is exactly one human-made machine sending back data from the space between the stars. It is 48 years old. Of the 10 instruments it launched with, 2 remain. Of those 2, one is the PWS. The PWS is listening to a hum that began in the middle of 2017, has never turned off since, and whose pitch is rising slowly but without pause. 9 years of continuous data. An 18-month magnetic hump recorded by both the PWS and the magnetometer in the year 2020, a density plateau that Kurth 2024 described with the words new regime, and at Madrid, 6 giant antennas are being turned simultaneously, only to keep listening. We have built things larger, more expensive, far more powerful, and none of them is telling us what Voyager 1 is telling us. Not because those things lack technology, because those things are not there. We have exactly one machine that has crossed the boundary and has lived long enough to truly listen. And the PWS is carrying the entire investigation on its shoulders. One day in the early 30s, the final hum will complete its journey to Earth, be recorded, and there will be no next one. The JPL team will close the control room. The question the hum is posing will remain open until the next generation dares to launch the next spacecraft. The final question I want to leave with you is not a scientific question. Humanity is mobilizing 6 giant antennas every day, only so as not to miss the update of a hum that is slowly climbing in pitch in the space between the stars. Not because we have to, because we choose. After this hum falls silent when the window closes for 25 years or longer, will we have enough memory to build the next window, a hum? 9 years, 48 years old, one chance to listen. The question is whether anyone is truly paying attention.